Hello, in this video I am going to be talking about the null space of a matrix. So the null space of a matrix is just the solution to the homogeneous system. I know that sounds very complicated, but it's actually really simple. So if we have a matrix A, the vector x, such that A multiplied by x is equal to the zero matrix, is called the null space. So the null space are vectors x such that if we have a given matrix A through multiplied by x gives us the zero matrix. Or if you want to write it in fancy set notation, you can write it as NA, where, so NA just means the null space of A, is equal to x, that's part of Rn. And when we say Rn, we mean, so for example, R2 would be two-dimensional space, R3 would be three-dimensional space, and R4 would be four-dimensional space, etc. So if a vector x is part of two-dimensional space, for example, it will have two rows. In three-dimensional space, a vector will have three rows, etc. So we're looking for the vector x such that A multiplied by x is equal to 0. So this is basically what the null space is. That's all it is. And a lot of you might be thinking, well, isn't the answer to this equation ax equals 0 just x is equal to the zero vector, so 0, 0, 0, so just all zeros. And yes, that is one solution. However, this is the trivial solution. So this is the trivial solution. And it's trivial because every matrix A will have this solution. So if I scroll down a bit, so what we want to do is find more interesting solutions to this equation. And the problem is that not all matrices A will have another solution. And in fact, only non-invertible matrices will have another solution. And so an invertible matrix, so invertible means the inverse of A exists. So any invertible matrix will only have one solution, and that is x is equal to 0. And this, quite simplistically, can be seen by if we pre-multiply both sides of the equation by a minus 1, we will get that x is equal to a minus 1, 0. And because a minus 1 exists and any matrix multiplied by the 0 matrix is 0, we get that x is equal to 0. However, non-invertible matrices, so matrices where a minus 1 doesn't exist, they will have other solutions. In fact, there will be infinitely many solutions. And we'll do an example now. So a non-invertible matrix means that the determinant of the matrix is 0. So in a sense, it squashes space into a smaller dimension. And if I generate a matrix that has a 0 determinant, so for example, I could have 1, 2, and then we'll have minus 1 and minus 2. 1, 2, minus 2, minus 1. So let's say we have this matrix here. So A is equal to this matrix here. And we want to find the null space of this matrix. So we will have, so we want the, so we have the equation ax is equal to 0. And we know what the value of, well, we know what our matrix A is. And so if we kind of write this in terms of like full matrices, and if we let x equal to PQ, then we will get 1 minus 2 minus 1, 2 PQ is equal to 0. And so if we simplify the left-hand side, we will get, so P minus 2Q, and then minus P plus 2Q is equal to 0. And so if we rewrite the right-hand side as 0, 0, we can equate rows of the vectors either side of the equal sign. So we will get from the first row, so if I just label these 1 and 2, from the first row, we will get P minus 2Q is equal to 0. So P is equal to 2Q. So it's better, P equals 2Q. And if we look at the second row, we will get minus P plus 2Q is equal to 0. And so again, P equals 2Q. And so the only necessity for a vector x to be part of the null space of A is for P to be double 2Q. And so x is equal to PQ, which is equal to 2Q, Q, which is equal to T to 1. So because Q is just a real number, we can say that the vector x is of the form T multiplied by the vector 2, 1, where T is part of the real numbers. And that's it. That is the null space of the equation. Some of you may be thinking, what's the point in finding the null space? Well, there are quite a few benefits of finding the null space of a matrix. One benefit is that it links into other theorems, such as the rank nullity theorem and just a variety of other theorems. But also, more simply, it allows us to find solutions to equations. So let's say I had the equation AX is equal to B. And I know that for this equation, Z is a solution. And by the way, we're just going to be using the same A as before, so A is equal to the matrix. So A is equal to 1, 2, minus 1, minus 2. So we know that Z, so let's say Z is a solution to our equation. And we want to know what are the other solutions to this equation, AX equals B. And in fact, all we have to do to get another solution is add any multiple of the vector 2, 1 to our solution Z, and we'll straight away end up with another solution. And the reason why this works is because what we're saying is, if we do A multiplied by Z plus T 2, 1, then we'll end up with another solution. And this can be seen because if we simplify this expression we have here, this is going to be equal to AZ plus A, then I'm just going to put in brackets, multiplied by T 2, 1. And so what's the value of AZ? Well, AZ is just going to be equal to B. And now what's the value of A multiplied by T multiplied by 2, 1? Well, if you think about it, by the definition of the null space of a matrix, this second term must be equal to 0. So this expression is just equal to B plus 0, which is then just equal to B. So as you can see, once we find the initial vector Z, we can then find infinitely many solutions. And in fact, the solutions to the equation ax equals b, so x will be of the form z plus t when 2. So all vectors x that are of this form here will be solutions to the equation ax is equal to b.